Okay, I've had a lot of questions about the sign conventions of lenses and mirrors, and let me just see if this video could clarify a little bit. I'm going to write 1 over the object distance plus 1 over the image distance equals 1 over the focal length. I'm also going to write then the magnification, which is defined as the height of the image to the height of the object, as, of course, negative Q over P. And it's really this equation and this equation, although maybe I should tie it together with that, that is really powerful, because if you're willing to accept some sign conventions, then we can use this same equation for all the mirrors. And so whether we're talking about a flat mirror, a concave, or a convex mirror, it would all work. Also, we could use this same set of equation for the lenses if you're, again, willing to learn some sign conventions. And so this equation works for the convex and concave lens. And they work no matter where you place the object. And so this is kind of this universal formula, and it's really, really powerful. And that's why I would say that it's totally worth committing the sign conventions so that you can always use this equation over and over again, whether it is for a mirror or for a lens. And so why don't I start with the mirror? Your book here has this little text box here, table 1, and it says, okay, when are these values positive and when are they negative? And let me start with the easy one. The height of the image, h prime, and therefore also the magnification, is positive when it's upright and negative when it's inverted. In other words, if I were to draw this picture here, if I start with, well, here, I'll just use the book. They've got a nice picture here of this convex mirror here. And so here is the object. The light bounces off and forms this image. And so right here, this image then is pointing up, so it is positive. And therefore the H is a, well, the H is a positive, but the H prime is also positive, which makes the magnification positive. So the sign becomes a little bit of an indicator of whether, what has actually happened. And in this case, a positive number would tell you it's upright, and a negative would tell you it's inverted. It looks like this image down here would be a good example of that. We start with H up, and then after the rays go through the mirror, they're now inverted. And so here's our definition then of the magnification. And so you have this whole idea then that if the magnification is a negative, or if H prime is a negative, it's upside down. So that's the easy one. If we then look at then maybe the, I'll call it the next harder one, if you will. But the Q could be either positive or negative. And that, like I said, would be where the image actually is. And so going back to this one here, you can see that the image then is over here in what we would call what your author calls the back of the mirror. I guess I like to say it's this part where the light didn't go, because I can use that same phrase for the lens. But see, the light came in and bounced off and went this way. And so if the image is formed over here where the light actually goes, which your author calls the front of the mirror, then Q is positive. But if the image is formed over here, what your author calls the back of the mirror, I'll call it where the light didn't go. So it only appears to have come from here. That's why we call it virtual. But it's also assigned a negative Q. So this would have a negative Q. So if we knew this value, we'd put it into the formula with a negative number. Or the other way around, if we're trying to figure out where it is and we solve for Q, and Q comes out to be a negative number, we know it's over here where the light did not go. It's on where what we call the virtual side, or what your author calls the back side of the mirror. And so that's what he means here when he says the front of the mirror. I like to say where the light really did go. The image is going to be formed after it reflects. And so looking at the light, where the light actually went, if the image is formed on the side where the light actually went, it's called a real image because the light really went there. And then it is a positive number. But if the image then is formed, and in this case we would say the back of the mirror, or the place where the light didn't come from, so in other words it just appears to come from there, then we would give it a negative number. Now, with that of course in mind, then, and this of course is the neat thing about this equation, that if you're willing to also accept positive and negative values for f, we can use this same equation, whether it be the concave or the convex mirror. And so we just want to kind of commit this to memory here. But if you look at f, we are going to call f a focal length if it is concave. And so in a mirror, well, that looks like this. This would be concave, or that picture I showed you earlier here. This would represent then a positive focal length. And the focal length would be half the center of curvature. So they call this the radius curvature of the mirror, and they put a C. So its focal length is actually half that, right about there. I like to say the focal length then is on the side where the light has really come from. And so it comes from this side and bounces off. And so if the light is on this side, it's a positive. And so it kind of has the same description as the Q that way to me. And so this is representing as a positive F. And in fact, just to kind of clarify then, so H prime is negative, but Q is on the side where the light actually got reflected to. So Q is a positive number here, and for that matter, F and R are also positive numbers. Whereas over here, this convex mirror is bounced off here, and the curvature, the radius of curvature is over here. Here's the radius of curvature, and here's half of that. Here's the focal length. So they're together, but also notice they're on the side where the light doesn't actually go. And so I use that phrase because where the light does not go, then would be a negative value for the F and the R, and for that matter, the Q. And so in this picture, we have H prime, which is positive, but we've got Q, which is negative, and we've got F that is negative, and we've got R that is negative. And so again, I like to use that phrase where the light didn't go. See, the light hit the mirror and bounced off. It didn't go over here. So after it hit the optical element, which in this case is the mirror, because I'm going to use that same phrase when I talk about the lens. But where the light didn't go on this side. It bounced off and stayed on that side. So things on this side, if Q is on this side, it's positive. If F is on this side, it's positive. If C, or the radius of curvature is on this side, it's positive. But in this case, the C, the F, and the Q are all on this side, so they're all negative in that picture. Now, by far, the hardest one of all is the P. When is the P negative? And let me point out then, that it says here it can be negative if the object is in the back of the mirror. And that could only occur with a second mirror, or a third or fourth or fifth. So if you only have one mirror, you can never have a negative P. And so the P would look something more like this. Here's where a negative P would come into play. Let me use this cap as maybe the representation of a second mirror. So this being the first mirror, as the light comes from our object towards the mirror, this right here would be a positive P. Then it bounces off and forms an image right there. And so if I were to put another mirror right here at this location, and so as the light goes from this image, which is the image from the first mirror, you can now treat this image as being the object of the second mirror. So if this was a second mirror, so it would be heading over here towards the second mirror. But you see, the image has already been formed, so the distance from here to here would be a positive P. And then, so if I was doing this calculation for the second mirror, from here to here would be the value of the P, and it would be a positive. The way you would get a negative is if this second mirror had been over here. You see, the image is not yet formed before it hits the mirror. If the second mirror wasn't here, it would form that image. So if we take away the second mirror, then it would, of course, form this image. But if you put the second mirror right here, you're actually putting the second mirror before the image is formed. Now remember, this image from the first mirror is now going to become the object for the second one. But this object for the second one, which is the image from the first one, is going to then, or the light is going to hit this mirror before it's actually even formed. And that's how you get a virtual object. The object never got a chance to get formed. And so the calculation would involve a distance of P, and P would be from the object of the second mirror. So the image of the first mirror is the object for the second. So from mirror number 2 to this, and again, I don't know if you want to call it the image of number 1, but I'd prefer to call it the object of number 2. So this object for this mirror is P, but I would treat it negative because the light goes this way, it never actually forms, it's virtual. That is the hardest one of all. So keep in mind, you can only get a negative P, first of all, when you have a second mirror or lens. And what you do is you place that second one before it actually gets formed. And we don't do that often, but it happens once in a while. Most of the time, we'd probably put the second mirror over here, or over here, or over here. And again, if it's way over here, then the image has already been formed. And so the P for the second equation would be from here to here. So this would be the distance between the second mirror and the object of the second mirror, which is the image from the first one. And so from there to there would be a P, and that would be a positive P. And so anytime the second mirror was over here, I'd have a positive P. I'd get a negative P if the mirror was over here. And I guess if the mirror was over here, there's no point even talking about a second mirror because light never even hits the second mirror. It bounces off the first, and the second one is just kind of irrelevant. So you can get rid of it for a weird case like that. So the second mirror would have to be between here and here for P to be negative. And if the second mirror was beyond this, then the P would be a positive. All right, well, I hope that helped, but I'll go ahead and switch over to the lenses. And the lenses kind of have the same logic here. There is a little bit different. I think the lenses are a little bit harder. But let me start with the easiest one, and that is the H, again, the H prime, the height of the image. And so if we take a picture of a lens, here would be a good one, maybe right here. Then here's the object. The light goes through the lens and then makes an image that is then pointing downward. And so H prime here would be a negative number. Or if we calculated the magnification, we would get a negative magnification. So it gets inverted here. Whereas in this picture here, here's our object, and the rays get bent around and forms this. Oh, I'm sorry, I said it wrong. This is the object. And the rays get bent around and form an image over here. And this image then is upright, so H prime would be positive. And this one over here, I think it's on the screen, right here. Again, here's our object, but the image is formed right here, and it's upright. So again, H prime would be positive. So I won't say too much more about that. Those, I think, are the easy ones. When is the H prime positive or negative? Now, the Q is, again, positive or negative, kind of like the mirror. One thing that's very different, though, is the light doesn't reflect because it's a lens, it goes through. And so coming back over to here, I would look at this picture and say something like this. I would say that the light actually went through the lens and the light actually then formed on this side. So this is the Q. The Q is from the image to the lens. And it's positive if it's where the light actually went. So the light actually goes through a lens. And so Q is positive on this side. Q is negative if the image is formed over here. And that's what we see in this second picture. Here, the light leaves here, gets redirected by the lens and goes this way. And so the light is on this side, but the light is appearing to come from over here. So this right here would be Q, the distance from the lens to the image. And that image then is the Q, but it's a negative Q. You see, this is formed where the light did not go. The light really went on this side. And the same thing on this third one here. This is the image. And so from the image to the lens is Q, and this would actually be then a negative Q. Again, because the light, once it hits the lens, went on this side. So any image formed on this side would be positive, because this is where the light really went. And on this side, well, this is where the light, I realize it started from, but this is not where it went. And so therefore, we are going to go ahead and call then this a negative. And so you could say this is the reverse sides as the mirror. And that's true, but I think that's kind of confusing. I think it's better just to say the Q is positive where the light really went. So for the lens, the light goes through the lens, and so the Q is positive on this side of the lens. Whereas way back in the mirrors here, the Q would be positive on this side of the mirror, where the light actually goes. So I like to say the Q is positive where the light actually goes, whether it is the mirror or whether it is the lens, where the light actually goes. And so hopefully that helps with the Q. Here's an interesting one, the focal length. Because here's where the lens is quite a bit different than the mirror. the mirror, the light, I'll go back to a mirror, but for a mirror, the light was only redirected one time, and that was when it bounced off the mirror. And so if we're looking at this mirror here, when the light hit it and bounced off, it was only redirected one time, and how much it was redirected was based upon its radius of curvature. And so the F is related to that radius of curvature. So in that equation, we have the focal length is equal to the radius divided by 2. But that is true only for the mirror. Because for a lens, the light is redirected twice. There's a Snell's law when it's going into the lens, and that's what this little example is trying to say here. And so when this being the object, oops, I go over here, and so this being the object here, if we start here, then the light gets redirected as it gets refracted off this first surface. Then it gets refracted again off this second surface. And so that's what they're trying to show here. And so they need to do it twice. That's why in this little derivation, they have, see, this little equation here for where is the image formed from the first refracting surface. And then they do it a second time right here and say, okay, where is the second image formed, meaning the image formed by the second refracting surface. And when they put the two equations together, they get this. And so I'll write that here in this equation, but it says 1 over f equals to n minus 1, 1 over r1 minus 1 over r2. And so it's not as simple as the mirror. The lens then may have a focal length that is positive or negative, depending on how this calculation works out. It depends on the two radius of curvature. So notice you could have two positive radii and yet still end up with a negative number here, whereas the mirror was much easier. When R was positive, F was positive. When R was negative, F was negative. They went hand in hand. But the lens gets a little more complicated here. And so to really understand this F, positive or negative, they just say here in this chart to say, well, okay, let's call it positive if it's a converging lens, and let's call it negative if it's a diverging lens. But as we, have here in these pictures, we've got to look at the curvature of each of them. And to understand whether the R is positive or negative, it's not listed in this table 3 because they listed it over here in this table 2 for a refracting surface. And so they say, let's call R positive when it looks like this, okay? And so when the curvature is over here, it's positive. I like to say it this way: the R is positive when the Q is positive. So what I just explained of when the Q is positive, so for the lens, the Q is positive where the light really went. So this surface right here would be considered a positive R. Whereas if it was curved the other way, which would be, in this example, curved this way, then as the light came and went out, this is where the light actually went. And the radius of curvature at 3 centimeters is where the light, originated from. It's not where the light actually went, and therefore that would be a negative R. And so sure enough, in his calculation right here, notice he puts a -3. And then, of course, he ends up with a negative Q. So back to our Q, notice that the Q then would be on this side where the light didn't actually go. The light actually went out of this little circular part into the human's eye here. And so a negative Q would tell me that it is on this side where the light wasn't. And likewise, the radius of curvature is where the light didn't go. And so if you had a lens that's got two surfaces, okay, something like this, then if our object starts over here and the light goes this way, it would hit this surface. So this would be a positive radius, number 1. And then as it went out, this would be a negative radius, number 2. Whereas something that looks like this one here, the light going this way would be positive and positive. Both of these would be positive. This one here, the going this way would be a positive R, and then, well, R would be infinity. So 1 over R would be 0, whether you want to call that positive or negative, wouldn't matter. See, this one here, as the light goes this way, would hit this surface, so that would be a negative radius. Then it would hit this surface, which would be a positive. And if it hit this one, this would be a positive and a positive. And if it hit this one, this would be a negative, and then this would be infinite radius, and so 1 over infinite would be 0. But that's really then how you get this F here. Now, there's kind of a shortcut your author likes to give you, is because if you just look at the overall effect of these two, that's kind of this big picture. In fact, anything that looks like these, all of these, if you do their calculations, you will get a negative number for F. And these three here will always give you a positive value of F. And so these will always make the light converge. These will always make the light diverge. I should say, at least if your light started as parallel light. If it was already diverging light, this may not make it completely converge, but it may make it diverge less. So it has a converging effect. And then this also, too, this makes the light diverge. And so if the light was already coming in and diverging, this would just make it diverge. I mean, if it was already coming out from something and diverging, then it would even diverge out even more. Okay, well, then we're back to the P again. And the good thing here is the negative P, although it's hard, the negative P is really the same answer as I just gave for the mirrors. So I'll run through it again, but I would say that keep in mind that the only way to get a negative P is with the second lens, or the third or fourth or fifth. You can never have a negative P for the first lens. And maybe I'll use, maybe this one here would be a good place to see as an example, because your object starts here, and it has your two focal lengths. The first one would have a positive focal length and then a negative focal length, which, by the way, looking at the formula, you would have then 1 over a positive, negative, 1 over a negative, and so that makes a positive. So overall, this would make a positive focal length. So this is a positive one. So this is a converging lens. And they're saying it makes this image. Okay. Now, if I took a second lens, and I'll just use this pin cap to indicate the second lens. If I put the second lens, say, right here, notice then that the light coming into the second lens is acting as if it was coming from this object. So the image of the first lens becomes the object for the second lens. And in this case, the light would have converged here, and beyond here would be spreading out. And so from here to here would be the object distance. This would be the P. And it would be a positive P, because, again, the image is already formed. The light's going in this way, and so the light is spreading out from our object of our second lens. This is the object of our second lens. Remember, this is the image of our first lens. So this is our original object. that original object, after the light goes through the first lens, makes this image. So this first image now is the object for the second lens. And so there to here is the P. And it's positive. In fact, anywhere over here, P would be positive. The only way to get a negative P is we put it right there. Then the light would actually be coming from the first lens and actually hitting the second lens before it can even make the image. So we still call the image of the first as the object of the second. And so from this image of the first, which I will now call the object of the second, so the object of the second to this lens right here, this is P. But because the light is actually hitting the lens before it gets to form, we call it a virtual object. And so in the equation, we would put a negative P. So we would want to know this distance, but we'd put it in as a negative number. So lens over here, this is P, and it's positive. Lens over here, this is P, and it is negative. Hope that helps.